Let's now look at prototype selection. We know that the size of the training set has a big influence on the complexity for making KNN classification. And so we know that with a really huge data set with n tending toward infinity, the algorithm tends toward optimal performances. So that's nice. We are able to get the optimal performances with really huge data set. But the storage processing time with such big data set is huge. In fact, it will be very heavy. So we often are not able to pay that cost of having such huge processing time and storage. Yeah. And depending on the position, you know, the density may vary. And in some regions, we may have a really high density. So we may not need to keep all training samples in that region. While in some others, you know, the density may be lower and we need to keep our samples that we have to be good at dealing with this region. So in fact, if we are looking at the decision boundaries with the complete data set, we can see that, yeah, it is important to have a good density close to the boundaries. But far away from the boundaries, we don't need to have that much samples, which are all from the same classes often. So we have a bunch of data from the same class, maybe just keep few of them, which allow us to make the right decision according to KNN classification, but we don't have to keep them, all of them. And also one thing we would like to get rid of is the outliers. You know, we may get outliers, noisy data, which are located in some places surrounded by training samples from data samples from other classes. So possibly we want to get rid of them because they are just inducing some classification error in terms of generalization. And as such, we may want to approximate the decision boundaries to get really good generalization still, but having much less representative, much smaller data set for computing, for doing our KNN classification. One approach for that is what we call the Hart condensation. The objective here is to select only data that are contributing to the classifications. We want to keep the data that are useful for classifying other than new samples, but we want to get rid of the others that are not useful for that. So we are making use of what we call an heuristic. So an heuristic is an approach that is not without any guarantee, but it is a good rule of thumb or a good routine that is making the job relatively well, without the guarantees that we got from a really formal, well-designed algorithm, but it is usually fast. And it is intuitive often as it does it, the way it is making the computation, it is relatively intuitive and the results are good enough in general. So Hart condensation is an heuristic that is making an incremental construction of the prototype. So basically it is starting from a most near empty with one sample per class data set, and it is adding on more samples as required for making good classification without adding anything that is not required. So if we have a sample that is already well classified and it doesn't change anything, so we are not adding it to the data set because it seems to be not required. So the approach with Hart condensation is to start with an almost empty set of prototypes. Usually we will take some randomly chosen data from each class, one sample per class, for example. And then we add only new instances if they are required to be for achieving a good classification. So we want to achieve perfect classification over the training set. So we want all the data set to be correctly classified with a subset of it according to the nearest neighbor rule. And we are repeating this as long as they are misclassified unselected data. So the point is that we are building up our subset until all training set data are properly classified according to the nearest neighbor classification. So more formally, in terms of algorithmic description, we have these things. So with Hart, we are creating a set of prototypes selected. So we are selecting, in fact, one data here. That's the point. It's not one per class. So we have one sample here that is randomly picked from our data set X. So this is the initial set from Hart condensation from which we are starting. And then, you know, as long as the Z data set here, which is at first the sample we took, as long as we are modifying it, we are continuing. So we are kind of applying this over the complete training set. So we are looking at each data set from the training set. And we need to do this in random order. That's important because the order at which we are processing our data from X change the results, change the outcome, and not to be dependent on some kind of arbitrary order. We need to shuffle the data set some way, or maybe need to process it in some kind of random order that is different from one iteration to another. And then we are, from each data in our training set, we are determining the closest neighbor in our reference data here. So we have our reference data set Z, that is at first only one sample. We are looking at the closest sample, which is X prime from Z, which is minimizing the Euclidean distance. And then we are looking at the class label of X prime. So if we see that the X prime, which is the closest to X, no, not X, in fact, the closest to XT here. So if it doesn't match the label, in fact, if the label of R prime is not the label of RT, then we are selecting XT as a new sample that we will add to Z. So if the data XT is misclassified, we will add it to Z. If it is well classified, we will not add it. And we are, in fact, repeating this as long as there is no modification to Z. So I would say, as long as Z is modified, that means that we added one or many samples to Z during our iteration here, we are repeating it. And once we are making a full pass on X here, without adding anything, so here I would say the labels are always matching, then we are stopping and we say, okay, now we are done. We have our subset Z built with all the samples required to achieve perfect classification without having extra samples that are already well classified with this subset. So Z is the prototypes selected in X. So this is one heuristic. We also have another one, which is looking at the problem the other way around. So with Wilson addition, we are looking at heuristics that will remove misclassified samples. So basically, it's more to clean up the data set, to remove the outliers, the samples that are disagreeing with the other samples we have in our data set. And so this is done by removing the misclassified samples according to a leave one out approach. So the point is to eliminate the data that are thought to be aberrant, noisy outliers. So Wilson addition proceed by starting with the full X data set as the set of prototype Z. And we are looping over this Z data set in random order. Again, we need to change the order, and this is random. This is important to randomize because otherwise the sequence may have a big influence on the outcome, and that outcome may be seriously disturbed by that. So we are looking at the k nearest. So here, contrary to Hart, where we are using the nearest neighbor, with Wilson, we are using the k nearest neighbors of xt in the dataset Z minus xt itself. So we are using a leave one out approach. We are looking at the nearest neighbors in Z to xt. And these are the k nearest neighbor to xt in Z. And then we are looking at the classification label of these k nearest neighbors of xt. And we are comparing it. So we are comparing the label from the k nearest neighbors in Z versus the real label of xt. And if these are disagreeing, so if we don't classify xt as the same class than the nearest neighbors, the key nearest neighbors, we are removing xt from z. So here we are simply removing the sample xt from the z because it is misclassified according to its key nearest neighbors. And we are in fact processing the whole data set in one pass. So we are kind of looping over all samples once, and that gives us the set of prototypes to keep, the ones that are, I would say, coherent together. So we hope with this approach that all the noisy samples that are disagreeing with their neighbors will be removed. We can even do more than this. We can combine these two together. So we can make what we call some kind of aggressive selection of prototypes. We can use Wilson addition followed by Hart condensation. So at first, we are removing the noisy outlier samples with Wilson, and then we will condense the resulting data set with Hart to really keep the ones that are useful. This can really remove a lot of samples, possibly that will hurt performance, but that will give us really a compact data set to use for KNN classification. So yeah, filter first the samples by eliminating the aberrant noisy data with Wilson. Select only the data that are contributing to the classification with Hart. And that's one approach. Another approach is called what we call prototypes building. So the idea is to determine synthetic samples, for example, that are not part of X, but that can be used for KNN classification. So this is kind of different from the one we are just explained. You know, Wilson Hart or Wilson plus Hart are really basic approaches where we just keep samples from our training set that are useful. Here with prototype building, we are considering to create new prototypes, create new samples to achieve good performance in terms of KNN classification. So one possible approach unsupervised is to, for example, applying k-means to X and using a high k value. So we want to get k-means with many samples. K-means is a clustering approach that we will see toward the end of the semester. So if we're looking here to illustrate the application of Wilson followed by Hart on the dataset that we had before, what we can see here is that the X's are data removed by Wilson. So we can see several outliers like this one. So we can see that these are really disagreeing. The color of the X is different from the region where they are located. So that's, I would say, illustrating well that Wilson is kind of cleaning up, removing all the outliers. Then we have the prototype selected by Hart. So these are the ones that are useful for classification. We can see, in fact, that all these squares are really close to the boundaries. And we have this one here, this one there, this one here, there. So we keep the ones that are close to the frontiers, but the ones in the middle, you know, okay, here we have a cluster of bunch of samples because you have this red region that is kept. But what we can see is that we have a bunch of circles here that have been removed. These ones are being removed by Hart because they appear to not be contributing to classification. And yes, indeed, because if we are looking at for example, that region here, we only need the one on the border to achieve good classification, and the other ones here are not that useful in the middle.